Hi everyone, my name is Hossein from EJ Academy and this video is about echelon matrices. If you don't care about the subject and happen to click on this video by mistake, don't be shy, just go ahead and skip this video. But if you're a random self-driven individual crazy about matrices, continue watching. Now that you decided to continue watching, let's begin by introducing a couple of terms, shall we? This is a 5 by 6 matrix, but don't panic, we're not going to perform matrix multiplication on it. I'm just going to use this matrix to define our terms. The first term is an entry of a matrix. Each element of this matrix is called an entry. The next term is leading entry. The first non-zero entry in each row of a matrix is called the leading entry. Having these terms defined, let's see what an echelon matrix is. An echelon matrix must satisfy three conditions. First, the leading entry in each row, if it exists, must be 1. As you can see in this matrix, the leading entries in the first 4 rows are 1, and the last row in this matrix does not have a leading entry. So the last row is exempt from this condition. Next, each leading entry in a row must be to the right of the leading entry of the previous row. This condition is also satisfied in this matrix, as you see. Even if on the second row the leading entry was on the second column instead of the third column, this matrix would still satisfy this condition. However, on the third row, if the leading entry was on the second column, this matrix would fail to satisfy this condition because the third row's leading entry would be to the left of the second row's leading entry. And finally, for a matrix to be an echelon matrix, the rows with all zero entries must come after the rows with non-zero entries, similar to what you see in this matrix. So this matrix satisfies all three conditions, and as a result it is an echelon matrix. There is a specific type of echelon matrix called row-reduced echelon matrix. This special echelon matrix, in addition to meeting all the conditions of an echelon matrix, must satisfy one more condition, which is the leading entry in each row must be the only non-zero entry in its column. In this matrix, the leading entry in the first, third, fourth, and fifth columns is the only non-zero entry. The extra condition does not apply to the second and sixth columns because there is no leading entry in these columns. Now that you know about echelon matrices, you can use the concept to solve system of equations using row reduction method. To show you an example, assume you have a system of 3 linear equations. This is the matrix form. Each linear equation in this example represents a plane in a 3D space. This matrix is a non-echelon matrix. If you transform it to a row-reduced echelon matrix, this transformation makes the planes more organized by orienting them in such a way that they would be perpendicular to the x, y, and z axis without changing their point of intersection, which is readily available from the row-reduced echelon matrix. There is a PDF file attached to the description below this video explains why the original matrix in this example is not an echelon matrix and how to transform it to a row-reduced echelon matrix using principles of row equivalent matrices. I have explained row equivalent matrices in a separate video, and I leave the link in the description below if you're interested to check it out. Leave your questions in the comment section and I'll get back to you as soon as I can. Thanks for watching. Cheers. If this video helped you in any way, please hit the like button and subscribe if you enjoy our content and would like to see more.